another aluminum base plate or a base metallic sheet, which can dissipate the heat further much more effectively. Now, we shall look at still bigger resistors. In fact, these are not the limiting values of the power wattages of the resistors. In fact, in the industry you will see that the wattage of the resistors can be as high as even 1000 watts, 10,000 watts and so on and so forth. But let me show you a 1200 watt resistor which is variable, which looks something like that. It is pretty heavy. Okay. So, let me place it here. Okay. You see that there are two cylinders. Are you able to see? I will hold it like that. There are two cylinders composed of wire wound wires. This gives the resistors. They are connected in parallel such that they can handle higher current and therefore more dissipation. This can handle something like 25 amps and they are 2 ohms, which means something like 1250 watts. Now, there is a lead screw arrangement here with a center tap which can move around here. I can vary this knob here and therefore change the position of the center tap. Now, the center tap is connected to this knob here. Okay. The one extreme terminal is here, the other extreme terminal is on this side, and therefore, you have the two extreme terminals and the third center tap terminated here. Okay. So, this is also a potentiometer, but in the high power regions of operation, these type of resistors are called rheostats. You can also get fixed resistors of such high powers also. So, now coming back to our topic of the basic components, we were till now looking at the resistor component, the one which dissipates energy. And if we go back to one of our earlier slides of energy flow, we saw that we were focusing till now on this component which takes away the energy or the energy that gets lost in flowing from the source to the load, and that component is the resistive component. Now, let us look at the storage components, that is the kinetic storage and the potential storage. Let us first look at the potential storage component, which is the capacitor. So, now what are the capacitors? Comparing with the resistor, we see that the capacitors are dynamic components. What does it mean by dynamic components? Means it can remember, it has history, it can store the past states or the past values, it can have initial conditions. That is what a dynamic component means. It is not algebraic, its present is based on previous values and therefore, they have memory. Now, the fundamental functional difference between the capacitor and the resistor is that this can store energy, whereas the resistor dissipates the energy, gives up the energy. So, this stores potential energy in the potential form. Okay. So, how does this store the energy? Let us look at a very simple analogy that we most of us would have seen in real world. This is a picture of a tub with an outlet at the bottom, and there is a tap which fills water, and the water is continuously flowing out through the bottom tap. Okay. So, the inflow and the outflow can so be adjusted that there is a particular height of water which is built up, and this is the buffer water. So, this water that is getting stored in this bucket is something like stored potential energy. In fact, that is how the concept of the capacitor can be related to this particular analogy. So, we say that the input flow of water is something like input flow of charges into the capacitor, and that is called charging, and the flow of charges out of the capacitor or flow of water out of the tub is something like discharging, the energy which is in the tub or which is in the capacitor that we are analogously calling. Okay. The capacity of this drum or bucket is analogous to the capacitance value of the electrical component capacitor, and the height or the head of water that is going to get stored in this bucket is the potential of the energy, and that potential is the voltage potential in the case of the capacitor. So, analogously this particular system which we probably see every day, bucket getting filled with water and then getting discharged, is will relate very well to a capacitance action. And the volume of the water is actually the charge that is put into the bucket or that is put into the capacitor. Now, the capacitor looks something like this in its most primitive form. It has two plates. There is one plate here, there is another plate here, and in between there is non-conducting dielectric material. Okay. So, the charges, let us say there is a current flow, the charges come and accumulate on this, let us say they are the positive charges, and then it will induce equal amount of negative charges on the other plate, and then there is a potential difference between these two plates, which is the potential. So, this charge accumulation is called the potential storage in the capacitor, which has a capacity C. So, that is the metal plate as I have indicated, this is the dielectric, this is the capacitor with capacity C, and the charge Q is current into time. The current into the time is the amount of charge that gets accumulated here, and the difference between the potential at between these two plates is the potential V or volts. Okay. So, here are the steady state equations for the capacitor. The charge Q is related to the current and time in this fashion. The current into time is equal to the charge. The charge is also equivalent to the capacitance or the capacity of the capacitor into the voltage V. Q is equal to CV, Q is equal to IT. These are fundamental steady state relations. The dynamic equations, the steady state equation is when everything is under stable operating conditions, nothing is varying, nothing is changing. In dynamic conditions, when there are transients, when there are step changes. So, these are the dynamic equations which are the more general equations. Under steady state constraints, you will see the earlier steady state equations coming into play. So, in the case of the capacitor, the voltage across the capacitor is remembered by the capacitance. So, the voltage is the state value. The current through the capacitor is always 0 in the average value. The average value of the current is always 0 in the capacitance under steady state conditions, but under dynamic conditions you will see that it is given by this equation, I is equal to C dV by dt, or the voltage is given by 1 by C integral of I dt. It is exactly this equation written in a different form. Now, this integral here implies that there can be history, there can be initial condition. So, the initial condition as far as the capacitance is concerned will be a voltage value. So, therefore, capacitor remembers voltages, it can remember the immediate past value of the voltages, and voltage is the state value or the state variable for the capacitance. And in the case of the capacitance, the voltages cannot change suddenly, it can only change smoothly or continuously. There cannot be a discontinuous change in voltage because of this fundamental equation, the integral equation. The V here on the left hand side cannot have a step change. The energy storage equation, we saw that the capacitor is a potential energy storage component. and therefore, what is the amount of energy that gets stored in the capacitance, and that is given by E, the energy, which is equal to 1 by 2 C V square or half C V square. You see that the energy storage variable is V here, the potential of the, therefore, it is the potential storage component, half C V square, and that can be obtained by simple derivation. We know that the wattage is V into I, and V into I into time is going to be the energy, watt seconds. So, integral of that over a period of time or over a period will give you the energy which is as given here. So, we say that as the capacitor has the voltage variable here in the energy equation, and its state variable or the state value is the voltage, or the history that it can remember is the voltage, which is the potential, and therefore, it is called the potential energy storage component. The capacitors also come in varied forms, varied types. There are different materials that are used in the manufacture of capacitors. So, you have basically two types, broad categories of capacitors: the polarized capacitor and the non-polarized capacitor. By polarized capacitor, what I mean is that there are two terminals, like in a resistor. One terminal should always be more positive with respect to the other terminal. So, that is a polarized capacitor. In the case of a non-polarized capacitor, either terminal can be more positive than the other terminal at any given point of time. So, there is no restriction that one terminal should always be more positive than the other terminal. In the polarized capacitor, the electrolytic capacitor is one which is most commonly used, and in the electrolytic capacitor there are two significant or more popularly used capacitors: the aluminum electrolytic capacitor and the tantalum capacitors. Tantalum capacitors are a bit more accurate in terms of the capacity. The aluminum electrolytic capacitors have lesser tolerance, meaning the variation is much more. It can vary from minus 40% to plus 100% than the value of the capacitor compared to the value of the capacitor that is written on the nameplate of the capacitor. In the case of the non-polarized, you have the capacitors named type named based on the material of the dielectric that goes into it, the ceramic dielectric type or the polymer based. You have the metallized polyester. Metallized polyester is something which is having very low tolerances to changes in the environment, and therefore, they are used for frequency tuning applications, things like that one. And this is the symbols that you normally encounter in the literature in the circuits, electric circuits for the capacitor. This is the most common symbol that you will encounter, two parallel lines with two leads coming out like that, and this is another symbol which is normally used for electrolytic capacitance, one with a thicker box type rectangular box type terminal, and another terminal which is a line. The box type has a plus there, indicating that it is a polarized capacitor, that has to be always positive with respect to the other terminal. And then you can also have variable capacitors with the arrow indicating that it is a variable capacitor. There is also a capacitor with the following symbol, which you also will come across in the literature: a terminal which is attached to a straight line plate, and another terminal which is attached to a curved plate. This also sometimes is used for electrolytic capacitors, that is polarized capacitors, with the straight line plate indicating plus and positive with respect to the curved plate capacitor. This is also one of the symbol that you would be coming across more commonly. Let us now look at some of the capacitors that you will find in the real world. If you look here spread out, there are a few capacitors, The smallest one here, this is a paper capacitor, and unlike again as I told you earlier that in the case of the resistors you have the color codes for the values, for the capacitors the values are printed on the body of the capacitor itself. So, you need not remember any color coding for this. So, this is normally used for decoupling in electronic circuits. This is another ceramic capacitor. These are non-polarized, these are all non-polarized capacitors here, what you see on the front. This box type here is a polyester capacitor used for frequency tuning applications. This has very low tolerances, meaning it does not vary much with temperature. Now, these two black capacitors that you see, they are polarized. They are what you call the electrolytic capacitors, and they are specifically here in this case what I have here is aluminum electrolytic capacitors. They are very frequently used in power supplies for actually holding the charges. They can hold large quantities of charges and they can come in very large capacities. So, these capacitors are in general used for actually holding the charges, whereas these capacitors also do the same function of holding the charges, but their application is more for frequency tuning, decoupling, things like that one. So, this is aluminum electrolytic. You see there is one short lead and one long lead, that is to distinguish the positive and the negative pole. But even otherwise on the body of the capacitor there will be a plus or a minus sign with put near the one of the terminal to distinguish it from the other pole. This is slightly higher capacity capacitor, which is as you can see something like 4.7 microfarad written on the body. There is also another value which is written here, 100 volt. All capacitors, there are two things that you will see on the nameplate. One is the capacitor value in farads or microfarads or nanofarads or picofarads, that will be written. The second number or the value that you will see on the nameplate is the voltage that it can withstand, because beyond which the dielectric will break down and then you will see that it will get spoiled or it will get damaged. So, you should not apply a voltage to the two terminals which is higher than what is written on the nameplate. So, which means that this is a 4.7 microfarad 100 volt capacity capacitor, and you should not exceed the voltage of 100 volts here. Now, let us have a look at few other capacitors that are bigger in size. Why should the capacitor be bigger in size? In the case of resistor, we saw that as the dissipation amount of heat that it has to dissipate increases, the size also increases. But here the capacitors are not supposed to dissipate, but still you see that they come in various sizes, right from small to the big. There are two things which are going to determine the size. One is the voltage. If you are needing to design a capacitance which is supposed to withstand a very high voltage, then also you need to have a dielectric in between which can withstand that field, which can withstand that voltage, and therefore, the size grows up. Then another thing is the capacitor gets polarized, and if the frequency of the polarization is high, then the internal molecules or the polarization zones which keep alternatively polarized, depolarized, polarized in one direction then the other direction, that will cause some heat called the equivalent resistance or the equivalent series resistance in the capacitance, which will cause some heat to get lost. Even though ideally a capacitor is not supposed to lose any energy, a practical capacitor will always have equivalent amount of resistor which will lose the heat because of the polarizing and depolarizing effect of the charges in the capacitor, and this will in general be represented the equivalent circuit as a equivalent series resistance or an equivalent parallel resistance, whichever one may want to use. Okay. So, an ideal capacitor is not lossless, it has some loss in it due to this practical limitations.